Hello and welcome to today's webinar, Support for Linux Control Groups, sponsored by Univa. My name is Neil Bender and I will be your moderator for today. Through our presentation, we encourage you to interact with us by typing questions and comments using the question panel. We will be answering questions live both during the event and after the presentation. Now to today's speaker, Daniel Gruber. Daniel holds a BA in Science and Master of Science in Information Engineering. He has worked at Sun and Oracle, and is now part of Univa Grid Engine development team. He's working on projects like Cgroups, Cray support, HP integration, Dharma 2, and so forth. So, Daniel, go ahead.
Okay, welcome to the Univa webinar about Linux control group integration in Univa Grid Engine. In January 2014, we released Univa Grid Engine 8.1.7, which contains, besides of bug fixes, also client-side JSV performance improvements and qsub-sync enhancements. Also, we have introduced a new feature called cgroup support. This webinar is about how cgroup support is integrated and can be used in Grid Engine. The webinar consists of 3 different sections. At the beginning, we will see how job isolation and resource limitation can be done with using the new cgroup feature. Then we will see a more detailed example how CPU sets can be used with Univa Grid Engine resource maps. Here the resource map complex type and topology masks are shown. Finally, we will conclude with inspecting how other cgroup systems, subsystems are integrated. So what are cgroups? Cgroups, or control groups, are a Linux kernel enhancement which aggregates and partitions sets of tasks into hierarchical groups with a specialized behavior. Such a group contains all future child processes. That means when a job creates a new process, it is automatically part of the same cgroup of the job. A cgroup associates a set of tasks with kernel subsystems. Subsystems is a Linux resource controller that schedules resources or applies limits on tasks. A hierarchy is a set of cgroups arranged in a tree. So why do we have cgroup support in Univa Grid Engine? It provides a way for irrevocable CPU and NUMA domain isolation. It also offers a way for safer job suspension and safe job reaping. It allows to limit main memory and virtual memory of jobs in different ways. The cgroups are deeply integrated in current Univa Grid Engine features. It is easily customizable by a Prolog script, which can do additional modifications of existing cgroups without the overhead for the administrator of creating and reaping the cgroups manually. The requirements for cgroup support are simple. You need to have a 64-bit Linux distribution. Depending on your distribution, you need a specific minimum version number. For Red Hat, we have a minimum requirement of Red Hat 6.0. The same is true for CentOS, Scientific Linux, and so on. With Ubuntu, you need to have version 12.4. On SUSE Linux, we tested it with 12.3 and so on. Basically, it works with any Linux distribution which offers a cgroup support. That means the only dependency from Grid Engine of cgroups is that you need to have these mounted subsystems and only file system access. There is no specific library needed. In order to use the cgroups, they must be activated. That usually comes with an additional package installation, which sets up a bootstrapping. That means when you're booting the host that those file systems are automatically mounted. But again, no library support is required. Of course, you also need the latest UNIVAC Grid Engine version 8.1.7. We are recommending the newest version 8.1.7 patch 3, which was released today. The supported features in UNIVAC Grid Engine are main memory limitation when using the mem3 resource, or virtual memory limitation when you are using the hvmem resource limit. But if you want to have automatic CPU set creation, then you need to request a core binding with using the -binding switch. For using the NUMA domain isolation, that means that a job can only request local memory, that means memory from the local NUMA domain, then you need to request the memory affinity, which was introduced in UNIVAC Grid Engine 8.1 by using the -mbind cores :strict parameter. This also requires to set a core binding. If you want to exploit the safe process sweeping when a job gets deleted or signaled, then you need this is automatically done and transparently for you. Process suspension without sending signals when suspending a job manually or automatically is also automatically supported in Grid Engine. You can override the behavior by using the suspend method in the queue configuration. We are currently supporting 3 different Linux subsystems: the cpuset subsystem, the memory subsystem, and the freezer subsystem. The cpuset subsystem is used for assigning CPUs and memory nodes to a set of tasks. It filters out the user-level system calls scat, set affinity, mbind, and set mem policy. Those were used before by Grid Engine in order to do a core and memory binding. Since a user can override this core or can do also these calls with traditional core and memory binding, a job can move from the assigned CPUs to other CPUs, which is now not possible anymore. In the CPU set, in the CPU set subsystem, you can inspect several files. 2 of them are cpusets.cpus, which contains a list of the CPUs in the CPU set. That means a list of processor IDs which are allowed for this particular job. If you inspect cpuset.mems, then you will see the memory nodes which are allowed to be used by jobs being in this C group. Memory isolation means the behavior of a group of tasks is determined by 3 different files. The memory.limit in bytes sets a hard memory limit for combined memory usage of the whole job. If you want to set a soft memory limit for the job or inspect the soft limit for a job, then you can do a cat on the file memory.softLimit in bytes. Memory.memsw limit in bytes is there for specifying the virtual memory limit. There is just a hard virtual memory limit configurable. The third cgroup subsystem we are using is the freezer subsystem. It is used for starting and stopping sets of tasks without signaling them. The current state of this cgroup can be seen in the freezer.state file. In order to configure cgroup in Grid Engine, you can either do that in the global configuration. If you have a homogeneous cluster, that means you have just one type of operating system, a Red Hat 6, for example, then you can do that in the global configuration. If you have a heterogeneous cluster, that means you have different operating systems or different Linux flavors installed in your Grid Engine cluster, then you need to configure that in the host local configuration. This example shows you how to modify the global configuration by the qconf-mconf global call. Here you can see a list of cgroups parameters. This is new in 8.1.7. If you did a hot upgrade from 8.1.6 to 8.1.7, then you probably don't see cgroups params. You have to insert that manually. This can be done easily by copying and pasting from the README of the 8.1.7 Univac Grid Engine release. Here you can see a list of parameters which manage the cgroups behavior. The first parameter is the most important one, the cgroups path. Here it points to the sysfs cgroup directory, which is in SUSE, OpenSUSE distributions, the default directory where the subsystems are mounted. If you type here none, then cgroup support in Grid Engine is completely disabled, regardless what you had configured for the remaining parameters. The remaining parameters like cpuset, mount, freezer, and so on are requiring either setting it to true or to false. You can also use 0 and 1 for configuration. The last parameter you can see here, the min memory limit, requires a memory specification. That means you can use here either integers, which are then representing byte values, or characters like M, which is here in uppercase megabyte. You can also use lowercase m, which is then a 1000 multiplier in Grid Engine. Cgroups. So what's going on then on the execution side in Grid Engine when cgroups are going to be used? First, the execution daemon tries to mount the cpuset, memory, or freezer subsystem if it is going to be used. This is only done when the mount parameter is set to true. Usually, the operating system should mount that during startup. But this is more to enforce it mounting in situations where it is not mounted. Then Grid Engine creates a UG subdirectory in each of the cgroup subsystems which are going to be used. Here in this example, you can see that in cpuset, memory, and freezer, a UG subdirectory is created, if it does not exist yet. The administrator can also create that manually and write configuration files and set configuration files into that directory. Those configuration files are in the top of the hierarchy later on for Grid Engine job. That means the limits are applied also for the job. But you need to be carefully what you will set in those files. So during job startup, a array job task or a per job directory is created with job number dot task number. Then all settings which have to be applied for this particular job are done in this cgroup. Finally, the shepherd process, which starts up the job, is put into the cgroup. Therefore, all child processes of the job are in the same cgroup. When a job is finished, then all processes in the cgroups are reaped. That means a kill signal is sent to them. Finally, the job-related directory is removed. In this example, you see how the cpuset subsystem can be used. Here, it requires just in the configuration to set cpuset equals true. Then the jobs needs to request the core binding either directly by using the -binding submission parameter or indirectly by using RSMAP topology masks. What this is, we will see later. In the example, you can see here 2 jobs are submitted. Each of the job is requesting 1 core. It is a binary job, that means it's operating system binary. Here the sleep binary is executed with the parameter 1, 2, 3, 4, 5. That's just the amount of seconds the process is sleeping. If you're inspecting now the cgroup which was created for the job, then you can see in the cpuset.cpus file that the first job, that means job 5, gets granted CPU 0 and job 6 got granted CPU 1. That means all sub-processes of that job are only allowed to use this particular CPU of this on this operating system. Here, the sleep binary does not fork anything. It stays anyhow on the same core. In order to limit main memory, you need to request the mmem3 complex. This one was introduced in Altair Grid Engine 8.1. It is similar to the mem3 complex, but it is initialized automatically during installation. It is a consumable and as well as and at the same time it is reported from the execution daemon. Here the grid engine logic always takes the minimum into account when the scheduler calculates if a job can run on a certain host. You have 2 different behaviors for limiting main memory. The hard limit produces an out of memory for the job if the job process exceeds the memory, if the job processes are exceeding the memory. When you have a soft limit, then the kernel would allow to exceed the memory if there is no memory pressure in the system. That means there is free memory in the operating system available. If now more processes are started from other cgroups or outside of the cgroups, then a memory pressure is in the system and the operating system, so the Linux kernel, forces that the job swaps out the main memory into virtual memory. Virtual memory limitation can be requested by using the -l hvmem request. Here in this example, we are requesting 768 megabytes. In order to prevent issues with too low memory request, so when you are requesting, let's say, just 1 megabyte of main memory, then you would have problems since the shepherd process could not be started up. In order to prevent such issues, you can configure in the cgroups configuration we saw before the min memory limit value. This memory limit is applied to all jobs if a job had requested lower memory. So in our example, when you are requesting 1 megabyte, the request is still visible in qstat, but on the execution daemon side, the job gets a limit of 300 megabytes set. In order to limit access to a particular NUMA node, you need to set in the configuration forced NUMA equals true. Then it requires a core and a memory binding for running the job. In Altair Grid Engine 8.1, we implemented a new resource type, which is called resource map or RSMAP. It is particularly useful when managing coprocessors and other per host and global resources. It can be used to isolate multiple jobs on one host from each other, so that there is no performance degradation due to other jobs possible. Now this has also cgroup support. Resource map can be used to schedule jobs to near resources. That is also called NUMA-aware scheduling. This allows you to have a lower latency for when you're requesting memory. It allows you to have a more flexible resource request, so you can decouple the per host requests from the slots request, which is a good thing when you're having coprocessors. It is implemented like a bag of strings, and the strings can be anything. In our examples, there are coprocessors. In particular, there are the numbers of the coprocessors. Then the scheduler assigns jobs to such strings. If you want to use the resource map resource type, then you need to declare the new resource. This is done by opening the complex configuration. In this example, you see a new resource type called phi, which is our new Intel Xeon Phi coprocessor. The type is set to RSMAP. The relative operator must always be like a consumable smaller equals. It must be requestable, and here now you have a new consumable type, a host consumable type, which is currently only implemented for the resource map resource type. Since our Intel Xeon Phis are more expensive, we're adding a higher resource urgency so that jobs requesting this complex are on the top of the pending job list. Now we need to initialize the resource capacity. Since we have 4 files installed on our host, we are adding here in the execution host configuration of the host mint with one command line for our 4 resources. It is initialized at the beginning like an int consumable type. Here we set phi equals 4. That means we have 4 instances. And then you can see the braces, which contains a list of strings. Here mic 0 to mic 3, which denotes the single instances of this phi resource map. You can do that also interactively by calling qconf-me and then min14 and then adding the complex values field or modifying the complex values field in the way like it is shown here. Of course, you can translate this example also to GPUs. Here in our example, job 12 is requesting one phi resource. Then the scheduler is looking into the resource map and figures out that there are all 4 mics which are configured for a particular host, for example, are free. Then the scheduler assigns the job the first mic which is found. Here mic 0. Now job 13 comes into the scheduler. The scheduler knows that mic 0 is already in use by job 12, so the job 13 gets now mic 1 assigned. The jobs can inspect this selected string or the mic number by reading out a specific environment variable. This is called, the name of the environment variable is SGE underscore HGR for hard granted resource, and then underscore, and then the complex name, like in our example phi. So SGE underscore HGR underscore phi points to the mic which is selected by the scheduler. From the outside, the user can see the selected mic by just typing in qstat-j and then the job number, and the qstat output will show you which mic was selected on which host. Resource map topology masks are an enhancement for resource maps, which provides a mapping of a resource to a specific compute core or a socket. It attaches to each instance, that means to each string, a set of allowed cores. It is written in or notated in the topology string format. You know already from the mTopology and mTopology in use resource, you can see in the qhost and qstat output. Such a topology string contains several characters. An S, which denotes a socket, a C, which denotes a core, and a T, which denotes a thread in case of inter-hyperthreading. Here in this example, the string SCC, CC, SCC, CC denotes denotes a system with 2 sockets and 4 cores. Now you can apply such a topology string, or how it is now called, a topology mask, because you can mask out cores in the complex configuration, in the complex values configuration. Here in this example, we see mic 0 in the string we saw before, and then just a colon and the topology string is attached additionally. This makes the scheduler now aware that when mic 0 is selected for a particular job, that then this job is only allowed to run on the second socket, because the first socket contains just smaller case c's, which is a hint for which denotes that those cores cannot be used. Therefore, the name is mask, because you can mask out cores by making or typing a smaller case c to the system. This is particularly useful when you are using or when you have NUMA systems because of the PCI Express NUMA device locality. So again, when you have coprocessors like GPUs or Intel Xeon Phi, and they are doing communication with such a coprocessor device, or you have 2 parts, one running on the host and one on the coprocessor part, then you have a lot of communication, and you need to make sure that the host part is running on a socket which is near to the PCI Express device where the coprocessor is installed. The following graphics should display or shows the logical layout of a current Intel 2-socket host. So on the left side, you can see socket 1, which has attached mic 0 and mic 1 through the PCI Express device. On the right side, you see socket 2, which has attached mic 2 and mic 3 through the PCI Express device. Now you can imagine that when you are having an application running on socket 2, but the application needs to access mic 0 or mic 1, that then the communication overhead is higher, because the application has to go over the quick path interconnect from socket 2 to socket 1, then going over the PCI Express device to the right mic. And this is what we want to prevent with the topology mask. The following configuration shows our 2-socket system, which has 4 Intel Xeon Phis attached. Here the host name is Maui. We have the complex name Phi, where we specify 4 strings, mic 0 to mic 3, like before. Additionally, we have now configured topology masks by a colon. Here, mic 0 excludes access to cores 4 to 8 on the first socket, and it also excludes access to all cores of the second socket. When mic 3 is selected for a job, then only the 4 cores on the second socket, the last 4 cores on the second sockets can be used, as you can see with the uppercase and lowercase c in the topology masks. Now you're wondering how you make such a mapping. It cannot be arbitrary. You need to know which mic is connected on which socket or on which core. This information you can find out usually in the sys file system. When you install an Intel Xeon Phi driver, then you will also have new directories in the sys class file system. Here you have the mic 0 directory, which contains the local CPU list and also a file NUMA node. And in those files, you can find the core numbers and socket numbers which are near to that device. It is very similar when you're having GPU devices, then you can also inspect the sysfile system and figure out which coprocessor or which GPU number is near which cores. Now when you are submitting a job, you just have to request the amount of coprocessors you are using. Here in this example, we are just requesting one coprocessor for our job 7004. When you're doing a qstat on that host, then you will see the new entry resource map. And here you can see that on host Maui, mic 1 was selected because before I submitted a job which was using mic 0. When you're submitting now a second job, or job 7005, then you can see that mic 2 is selected. Now when you log in on the execution host, inspecting the CPU set for that jobs, you will see that for job 7004, the CPUs 4 to 7 and 20 to 23 are selected. So we have now 8 core IDs or 8 processor IDs, but we configured a mask of 4 cores. How can that be? This is simply because here on that host, hyperthreading is turned on. So you will see the virtual core IDs or virtual processor IDs here, which is double the amount of cores. If you're now inspecting the local CPU list of the mic 1 device, that you can see that it is a superset of the selected cores for that job. So now we are sure that our job runs near our coprocessor resources. Other subsystems which are integrated or used in credentials is the freezer subsystem. It is used for job suspension and job resume. A traditional suspend and resume of a job is working by sending SIG stop and SIG con signals to the process group. This can lead to several problems. First, it is visible to the job. So for example, the SIG con signal could be trapped by the job. And the job stays then suspended, even credential wanted to resume the job. You can also have issues when sending SIG stop and SIG con cascades. An alternative is now using the Linux freezer subsystem, because it does not send any signals to the job. That means it is completely transparent for the application. All what you have to do is to enable the freezer equals true in the global or host cgroups configuration. This behavior is overridable in the queue configuration when you have applications which rely on specific signals, and on the other side you want to use the freezer subsystem. Then you can use a specific queue for that such parallel processes, for example, or MPI processes, which can usually or catch usually a specific signal, the TSTP signal. All processes of a job are excluded from being scheduled when suspended, and they are frozen by the freezer subsystem. You can influence the behavior for parallel job with the freeze PE task settings. You can freeze the master task if it is set to false, and if you want to freeze all master and slave tasks of a parallel job, then you can set freeze PE tasks equals true. Finally, we exploited cgroup, a cgroup feature in UNIVA Grid Engine for job reaping. So all processes started by a job must be stopped when a job is finished or exceeds limits or is deleted manually or automatically. When a job is rescheduled, it must be reaped as well. And finally, when a master task of a parallel program is finished or exited, it must also be reaped. The default behavior of Grid Engine is sending a kill signal to the process group of the job. But this can lead to leftover processes. One example would be when you are submitting or when you are requesting a GVIM session via qremote shell. Then the GVIM itself creates a new session and a new process, and therefore also a new process group. And this is not tracked then from Grid Engine anymore. Then you will see that your GVIM session keeps open while the job is already finished. A solution was implemented a very long time ago by a specific execution daemon parameter called enable additional group ID kill equals true. And what this means is that when you installed Grid Engine, then you have provided a range of additional group IDs for the execution daemon. And each job in the execution daemon, when a job is started up, then it selects a free additional group ID for this job and attaches this additional group ID to the job. That means all child processes of the job are having the same additional group ID. Now, when the execution daemon wants to reap a job, it does not send a signal to this process group. It goes through the proc file system and looks for processes which contains or have this additional job group ID set. This way, it is guaranteed that Grid Engine finds all processes which are part of a job. But at the same time, it can lead to hard to track issues. For example, when you have applications which are also using additional group IDs and you don't know about that, then applications could attach different additional group IDs which can overlap with the Grid Engine additional group IDs to other processes. And then Grid Engine could kill more processes than it should. Therefore, we disabled this in a default installation, and the user or the administrator must enable that by default. They must enable this manually. Now, a solution for this is setting the killing equals true cgroups parameter in the Grid Engine configuration. What Grid Engine execution daemon now does is it tracks the tasks file of a cgroup. So all cgroups containing a task file which contains all process IDs which are part of a cgroup. That means with using that file, looping around that file and sending a kill to all processes until this file is empty, this guarantees that only processes which belong to a job are signaled. You can also not signal too many job processes because they are not part of the UNIVA Grid Engine cgroup hierarchy. It guarantees that only process IDs which belong to a job are signaled. So in order to summarize this webinar about cgroups, we can highlight that cgroups in UNIVA Grid Engine can be used for isolating jobs. There is no performance degradation due to badly behaving jobs than possible anymore. Grid Engine schedules jobs near resources by exploiting the resource map topology masks. You can also use the cgroups integration to restrict main memory usage of application. It offers a complementary way for a safe job suspension and a job resume. It offers also a complementary safe way for cleanup of job processes. Finally, we do our future enhancements based on customer feedback. So thank you very much for your attention.
Okay, thank you, Daniel, for the presentation. Guys, if you have any questions, you can email us at sales@univa.com. On behalf of our guest, Daniel Gruber, as well as the folks over here at Univa, thank you for joining us and taking the time to view the presentation. Again, thank you. Bye.